Well, good morning, everybody. My name is Elise Brown. I am the Assistant Director of the Policy Institute for Energy, Environment, and Economy, and also the Associate Director of the California Geothermal Energy Collaborative. This morning, we will be hearing a presentation from Dr. Bill Glassley on the efficiencies of geothermal heat pumps in California by climate zone. Dr. Bill Glassley is the Executive Director of the California Geothermal Energy Collaborative and also a researcher in the Earth and Planetary Sciences Department here at UC Davis. The format today will be a half-hour presentation from Dr. Glassley, followed by roughly a half hour of questions and answers. If you'd like to ask a question, you'll see the chat box on the left-hand side. You can go ahead and ask it there, and then I will moderate the question and answer session when Dr. Glassley is done with the presentation. There's also a policy brief accompanying this webinar on the webinar website. You can access that by going to policy.ucdavis.edu. And after the presentation, we will post the webinar video as a YouTube video. So if you have colleagues that would like to view this, you can direct them there. For now, I'm going to go ahead and turn it over to Bill Glassley.
Thank you, Elise. It's a pleasure to be here and to have the opportunity to talk about geothermal heat pumps. I would like to begin first by acknowledging my co-authors, Elise Brown, Adam Asquith, and Tucker Lance, who were very instrumental in producing the information that I'll be talking about. I would also like to acknowledge the California Energy Commission PEER program for providing the funding to support the work that I will be talking about, particularly toward the end of the presentation as it relates to the state of California. The mission of the California Geothermal Energy Collaborative, as established by the Energy Commission when the collaborative was first set up a number of years ago, was to provide the opportunity for stakeholders or people interested in geothermal energy in the state of California to have a venue in which to talk about issues related to geothermal energy, provide an opportunity for outreach and education to the communities in California, to support research and industry needs as related to geothermal energy. We have undertaken a number of research efforts, and many those have been published in a variety of venues. Much of that is available on the website if you are interested in more information. As an example of the kind of programs or research that we've undertaken, this is a list of some of the things that we have done, and most of this is available also through the website. What I will be talking about today is the study we did statewide for California related to large-scale deployment of geothermal heat pumps. This was a study that was complementary to a national study that we did that was funded by the Department of Energy in collaboration with Bob Lawrence and Associates. In that case, we looked at the cost benefit of deploying geothermal heat pumps in 30 metropolitan areas around the United States. In the presentation I'll be giving today, I will be focusing exclusively on the state of California and the results of the study we did that related specifically to that. So the way I will organize this presentation is first just talk about a little bit about the energy use in the state of California and some of the policies and issues that the state faces. Then talk a little bit about geothermal heat pumps, also known as ground source heat pumps. There are a variety of names that are used to describe them, but essentially how they work, why they work, what their characteristics are. And then I'll spend a bit of time talking about the results of the study we did, how it was set up and what the results were, and their implications for the state of California. California, on average, uses about 20% of the total energy consumed in the state for building, heating and cooling, and heating hot water or heating water. One of the things that is important to realize, therefore, is that for every % change in energy reduction used for heating and cooling buildings translates into essentially the equivalent reduction in energy that would need to be produced by the state. This is important because the state of California has established a renewable portfolio standard in which the goals are to reduce by 33% the amount of energy that the state generates and have that replace 33% of the energy the state generates by renewable energy resources. That's a very important and daunting goal. It's something that has established standards for other states around the United States, and California is the model for how to achieve that kind of standard. An additional mandate that the state has established is the reduction of greenhouse gases. The standard as it currently is structured is to have eventually achieve emissions in the state that are 20% below the 1990 levels. In order to accomplish that, renewable energy resources need to replace fossil fuel energy systems. Geothermal heat pumps are one way of accomplishing and contributing to these goals. What I hope will be the takeaway from this presentation is the magnitude of the impact that geothermal heat pumps can have, why they are a very, very important means for accomplishing those goals. So let's quickly look at why these systems work. The graph that you see is a graph. Vertical axis is depth into the earth from in meters, from 0 meters down to about 15, which translates to about 50 feet. Horizontal axis is temperature. That's the air temperature. That's the temperature at whatever the depth is of interest. This figure was developed on the basis of work researchers in Sweden did, and it relates specifically to the Swedish environment. The patterns that I will describe exactly relate to similar patterns in other parts of the world. The only difference is where along that horizontal temperature axis the curves would fall. Let me walk you through them and describe what this shows. The right half of the figure represents summer conditions. The light black, the thin black lines represent how the temperature would vary for two different soil types from the ground surface here to depth here. That curve is for a light dry soil. The other curve is for a heavy wet soil. The point that's important here is that during the summer, because of the sunlight and warm air temperatures impinging on the ground surface, temperatures are close to, in this case, 16 degrees centigrade, which translates to about 70 degrees in the air. As you go down, temperature decreases and eventually reaches a constant value at some depth. Where on the planet you are, that constant temperature is achieved will vary from place to place. But the important point is that the temperature here is lower during the summer than it is on the ground surface. During the winter, these light curves are the ones that are of interest to us. And in this case, if you're in Sweden, temperatures are going to be below freezing, which is below 0 degrees centigrade. It's going to be cold. But as you go down into the earth, the temperature increases until eventually you reach that constant value. The solid lines represent measurements that were taken during 2 different years, and they show how the real measurements follow very closely the pattern seen from theoretical calculations, which is what the light lines represent. Critically important in this is the fact that during the summer, the air temperature and ground surface are warmer than this region, which means that this area can be a heat sink if it's possible to move heat from here, from a building, down into the ground. During the winter, just the opposite is possible. The air temperature is cold. This region could be a heat source. Moving heat from this area up into the building can be accomplished providing you can move heat. This is the basic fundamental characteristic of natural systems that allows geothermal heat pumps to be so attractive. Moving heat is much more efficient than making heat. And it's another reason why geothermal heat pumps, and is the fundamental reason why geothermal heat pumps are so attractive from an efficiency point of view. Whether you're dealing with a liquid fuel like gasoline, you're dealing with a gas, or you're dealing with a cold solid, in order to obtain heat from these, you have to ignite them and generate a gas phase. This process of ignition is fundamentally inefficient. Heat is lost as a result of entropy, which can be considered disorganization of materials, movement of molecules. Heat is lost through a variety of poor insulation characteristics associated with whatever whatever method is being used here to generate the heat. And in addition, every one of these essentially fossil fuel energy sources requires a fuel cycle, where you obtain the material, you process it, whether it's mining, refining, whatever it is, and then you transport it. And all of those contribute to a low efficiency in using fossil fuels to generate heat, to use heat. Geothermal heat pumps pump heat. They move it physically from one place to another, and it's exactly the same process as takes place in a refrigerator. Everyone has a refrigerator, most people do, and they are a device that pumps heat from the interior of the refrigerator into the room. If you ever have gone to the back side of an operating refrigerator, you know it's a very warm place. There is a small heat pump within the refrigerator that moves heat from the interior and dumps it into the room. The room is the heat sink, the interior of the refrigerator is the heat source, and the pump just moves it from one place to another. It does it very efficiently, very quietly. Most of the time you wouldn't even notice that it's running. It's exactly the same kind of situation as with the geothermal heat pump. The way the geothermal heat pump operates is through a simple phase change. And this figure shows how a phase change operates and what it means in terms of energy. If we take a solid like ice, basic ice cube, add heat to it, it melts. But in the process of doing that, that ice absorbs heat. Eventually, if you heat it up enough, it becomes vapor. That vapor has in it the heat that was put into the ice. If you then transport that water vapor to a place where you want to freeze it again, the heat that was contained in that vapor is released. In other words, you have a cycle in which heat is put into the water becomes vapor that can then be transported someplace and then frozen again, and the heat carried from that initial heating of the ice is released, and it's a way of transferring heat. It's highly efficient. For a heat pump, this is what the system looks like. It's a lot more complicated, but it's the same process. On the right-hand side, that's where we go. On the right-hand side, this coil represents a loop that goes to the ground, down to that level where the temperature is constant. In that coil, we circulate water or some other solution. That water goes down to that place in the ground where the temperature is more or less constant, equilibrates with that region, and then circulates back to this environment. It's transferring heat from the ground to this location. Now, what's shown here in this circular or oblong thing is essentially a closed-loop system, a separate one. Contained within it is a liquid like isopentane or isobutane, propane. It could be a variety of different things. But it's a liquid or a gas phase that has a very, very low boiling point. Boiling points on the order of 5 degrees, 10 degrees, 20 degrees Fahrenheit. This loop let's say it's at 55 degrees Fahrenheit. If it's in contact with this closed loop of our isopentane, that isopentane, when it gets to this point, will heat and boil and become a gas phase. It'll become a warm gas phase. And what it will have done is taken heat from this coil, and that heat has been transferred to the gas phase. That gas phase then moves through a compressor. The compressor pumps it up to a higher pressure. What that does, in essence, is it does work on the gas, adds energy to it, a little bit, incrementally adding energy to that system, and that hot gas then moves into the room where there is a heat exchanger. At C, where the arrow is, heat is taken out of that liquid through a heat exchanger, or that hot gas. That heat is put into the room. At the same time, that hot gas is cooled because the heat is taken out of it. It condenses, becomes a cool liquid, goes through this decompression valve, which allows this high pressure liquid, this high pressure or moderate pressure cool liquid to go through the valve. It loses even more energy, becomes cooler, becomes a cold liquid, flows back to the coil where it picks up heat, and it starts the cycle all over again. This, in essence, is a geothermal heat pump. You can run it in this mode, which is the heating phase, or you can run it in our cooling phase, in essence, just transferring, instead of transferring heat from the ground into the liquid, the heat is transferred from the liquid into the ground. This is an example of what these systems look like when you're actually looking at them in a three-dimensional view on the ground. This is a building, it's a home, let's say, and there are multiple configurations in which it's possible to set these loops up to extract heat from the ground or put heat into the ground. This is one loop or one style in which a trench is put into the ground, a flexible polyethylene tubing of some kind is put in kind of like a slinky, layered out, and eventually allows the fluid to circulate into the ground surface, contacting the ground, exchanging heat or taking heat out of it, moving it into the house where the geothermal heat pump sits. Another configuration allows boreholes that go deep into the ground to be the place in which this tubing is placed to allow fluid circulation for heat extraction or heat deposition. Some of these boreholes can be borehole fields. They can be of a variety of depths. There are a number of ways of installing these. Newer systems are being developed that allow relatively large diameter, shallow boreholes to be put in with a complex of pipes that are compressed similar to what exists here, but it's oriented in a vertical fashion. A variety of configurations. The important thing about these is that the style you use depends upon what your situation is, how much land you have available, and what your budget will allow. The cost of these systems is changing quickly. They used to be extremely high cost. They are becoming much more moderate as a result of a variety of new styles and strategies for employing them. So they're from a market point of view, they're becoming more and more attractive. One of the things that is important about these systems, though, in order for them to work, is that they need to be designed very, very carefully. It is one of the things that you must, in order to have a system that's going to be efficient, you need to work with somebody who understands these systems and understands their constraints. One of the important issues with geothermal heat pump systems, in order for them to function at their highest efficiency, is for the system to be designed taking into account local characteristics. And one of the characteristics is the ability of the soil to transfer heat efficiently from the soil itself into the piping that's used for the geothermal heat pump. Now, how well that happens is what is known as the thermal conductivity. in order to know how long you need your piping system to be, you need to understand the thermal conductivity of the soil that's in your area. What's shown in this graph is a borehole or depth. It's in meters on the left-hand axis, in feet on the right-hand axis. And the horizontal axis is temperature in degrees centigrade, temperature degrees Fahrenheit on the upper axis. If you're in Boston and you put a borehole down into the ground, almost any place you go, the temperature is going to be highly predictable as a function of depth. There is not much variability. And that's a really important point for the Boston region. There's not much temperature change, as you can see as you go down. If you're in Dallas, you still have highly predictable temperatures, almost a linear function of depth, not much scatter, but the temperatures are higher, reflecting different geological conditions. In these two environments, these two situations, it's possible to design these systems and have some confidence in them if you're using a rule of thumb approach. You know what the load characteristics are of the building you're going to be designing for. You know something about you'll be able to predict highly effectively, efficiently what the thermal conductivity is as a function of depth, what the temperature is as a function of depth, and so the design is simpler. In a place like Los Angeles, on the other hand, and this is true for many places in California, temperature as a function of depth is highly varied. So it means that you need to actually, rather than operate using a rule of thumb where you have a linear approach, you need to go out and do some measurements, collect some samples, understand what the system is, or at least have enough information from the local area so that you'll be able to have a good idea of what the system is like. On the basis of that, you can come up with some efficient design. California, fortunately or unfortunately, depending upon your perspective, has a complex suite of environments. There are 16 different climate zones, and that's what's shown in this figure, in the state of California. The blue climate zones are zones that are predominantly cooling loads. The yellow and greenish zones are zones that are predominantly heating zones. That means that it's important to understand the climate zone you're in when you undertake the process of designing a system, because what the load is going to be is going to depend upon where you live in the state of California. What we did in the study we undertook was to come up with a standard building and then model its behavior in all of the 16 climate zones. The building we started with was the standards we used for its characteristics and properties in terms of insulation and building construction quality were the ASHRAE Standard 2007 standards. The building was the average home in the United States, 1,934.2 square feet. Please appreciate the precision that we bring to this effort. It was a rectangular home oriented east-west. Occupancy was assumed to be 2.6 people. That is the average building home occupancy for a house in the United States. We assumed the same applied in California. To do the load calculations for the building for each of the climate zones, we used a software package called eSIM, which Dr. Kissick at the University of Dayton has made available. It can be downloaded from the internet. And then the system design, we employed the GLD software that was produced by Thermodynamics. They are a major company involved in geothermal ground source heat pump system design. This graph shows the energy consumption for each of the 16 climate zones. And the way it does it is the horizontal axis shows how many kilowatt hours per year would be consumed for heating and cooling a home if one used a geothermal heat pump system. The vertical axis is the amount of energy that would be consumed for that same home in that same climate zone if one used the conventional HVAC system. Take an example of how to read this. This point represents climate zone 13. if you were in climate zone 13, this is saying that in that zone, you would consume about 8,000 kilowatt hours per year for heating and cooling the home if you had a geothermal heat pump system. For a conventional HVAC system, though, you would consume something on the order of, let's say, 13,000 kilowatt hours. In other words, a difference of almost 50%. A 50% reduction in energy use if you employed a geothermal heat pump system as opposed to a conventional system. In fact, any point that falls above this heavy dashed line represents an energy savings for installation of geothermal heat pump systems relative to a conventional HVAC system. Climate Zone 15, which is in the Imperial Valley, is predominantly a cooling environment, and in that situation, the heating and cooling efficiency, at least at the time we modeled these systems, the heat pump in cooling mode was not as efficient as the standard HVAC system at the time. This study was done several years ago. Geothermal heat pump systems have increased in efficiency tremendously. If we were to redo this study now, all of the points would fall above and to the left of this heavy dashed line, including the Imperial Valley. In other words, energy savings would be achieved by any climate zone in the state of California using modern technology. The light dashed lines represent the energy saving percentage. They're essentially contours, so anything along this line would be a 20% energy savings. Anything along this line is 50%. Anything along this line is 80%. One of the things that's striking about this graph is the broad range of results one can have depending upon the characteristics of the local climate zone. This table shows by climate zone and representative city what the results were, conventional energy consumption, GHP energy consumption, and what the difference is, and essentially the energy savings or reduction. Average for the state was 44.26%. In other words, the state of California, if geothermal heat pumps were deployed consistently in a broad way, would save about 40% in its total energy just for building heating and cooling. In terms of emissions, and this gets back to the AB 32 goals, this graph is similar in the sense that the horizontal axis is for geothermal heat pump use, but in this case the units are kilograms of emissions per year, combined CO2, NOx, and SO2. And this comes from the energy, the electricity generated to power the geothermal heat pump systems. And these are the emissions for a conventional system, again in kilograms per year. And again, anything that falls above that heavy dashed line represents a savings or a reduction in emissions. And the percentage savings are very similar to what you saw on the energy consumption graph. Logical, because the amount of energy you consume is going to also have a direct effect on what the emissions are for that power consumption. So geothermal heat pump deployment not only would help meet our RPS goals, it would also help meet AB 32 goals, greenhouse gas reduction. So the principal observations that we came up with as a result of the study that we did. First of all, the average household in the state of California consumes something on the order of 6,000 kilowatt hours of power, and by deploying geothermal heat pumps, that would be reduced to about 5,000 kilowatt hours. Significant savings. In terms of the savings range, the savings can be as high as 77%, depending upon the climate zone you're in. That's a tremendous energy savings. Most of these, the greatest of energy savings occurs in regions that are predominantly heating load. These savings would be higher today than the time we did this study because the efficiencies for these systems are much better than they were in the past. If you translate this into what the impact would be for the state able to meet its RPS goals, the amount of energy that the state would have to produce would be the amount of energy that would have to be produced by renewable resources, and also the amount of energy that would have to be produced just by conventional resources would be reduced by about 10 to 15%. In other words, deploying geothermal heat pump systems lowers the energy demand and makes it easier for the state to meet its RPS goals. Finally, in terms of greenhouse gas emissions, geothermal heat pumps would provide an important contribution to reducing total emissions in the state. Because they are relatively easy to install and can be installed quickly, they also provide a very easy way of moving rapidly towards achieving those same goals. So, in conclusion, geothermal heat pumps really can make a difference. Having them deployed broadly around the state could have significant impact on both energy and emissions goals that the state has. Best performance is in regions where heating is the primary load. One point we would like to make, and we think needs to be emphasized, the modeling we did assumed building standards that were in place around 2007. Buildings built before that, the standards are not as good. That means that much more heat is lost, heating demands are higher, and cooling demands are higher at the same time. Deploying through retrofits geothermal heat pump systems through older buildings can result in even more impressive savings, both in terms of energy consumed and in terms of emissions. The one thing that as a caveat, we would like to emphasize here is that designs need to be done well. These systems are they're high-tech systems. They require thoughtful design. They require knowledge of what the load is going to be. They require knowledge of what the local environment is. Make sure if you are going to be using a geothermal heat pump system, you work with a reputable installer and designer. The upfront costs for these systems can be substantial, but they are coming down very, very quickly. Changes have taken place dramatically since the time we did the study. The costs for these systems are now competitive with most other systems that are available. Those are the principal conclusions we have for this study. I would like to emphasize the results are available on the collaborative website, as well as both for the state of California and for the national study. I would be happy to entertain any questions. If you'd like to contact me at some other point, my contact information is here. Thank you very much for the opportunity to present this information.
All right. Well, thank you, Dr. Glassley. We have received a few questions via the chat box. Just so you all know, they are anonymous. So if you have a question and you maybe don't want people to know where you're from, we won't say who asked what. So please go ahead and continue to ask questions in that chat box. Just it's chat with presenter, and you just type in your question and hit send. One of the easier questions to tackle is, will this presentation be available after the webinar? And if you go to policy.ucdavis.edu, click on webinars, and then geothermal heat pumps, you'll see not only this presentation as a YouTube video, but also the slide deck, as well as a policy brief and the paper that this presentation is based off of. All right, Dr. Glassley, we do have a question about slide 5. And the question is, what is the source of the 20% statistic? So the 20% statistic stating that California uses 20% of its energy consumption on heating and cooling buildings.
Off the top of my head, I don't remember the exact source, but I believe it was I think it was a CPUC statistic, California Public Utilities Commission, and that represents the average value for the state. Because the state has so many different climate zones, that number, that 20%, varies tremendously from region to region. It's almost as broad as the results we had in terms of energy savings. but 20% for the state of California. Not in terms of, that's for the total number of homes, and represents essentially the average based on that.
All right. The next question has to do with the emissions saved. Because in geothermal heat pumps, you are shifting from, oftentimes, in the case of heating, you're shifting from natural gas to heat. You're switching to electricity to run a heat pump. The question states, did you use an average of non-renewable and renewable derived electricity in your calculations? How did you come up with that?
The CalISO produces a yearly summary of what the mix is of resources for generating power in the state of California. We took the CalISO numbers for, I forget which year it was, I think it was 2010, and on the basis of that energy mix used FERC numbers for calculating what the total emissions would be based on the energy source.
Okay, great. There's a question, why was Zone 16 made so large, and will it be broken into subzones in the future? How did you come up with climate zones?
The climate zones were established by the state of California. I don't remember which agency it was, but they were established a number of years ago. And we simply took their designation of the climate zones and used those as the basis for our modeling. I do not know if there will be any finer grained effort to make those climate zones smaller and each one more homogeneous. I don't know where that's going.
All right, yeah. So they were predefined.
Yes, they were predefined. We did not define them.
All right. Let's see here. Next question. Geothermal heat pump installations in California are minuscule compared to the Midwest and the East Coast. What, in your opinion, are the reasons for this?
Complicated question. I think part of it is the fact that in the Midwest especially, but you could also see from the numbers we had up there for Boston, the subsoil conditions are really consistent. What that means is that it's easy to design a kind of rule of thumb design system. That means that you eliminate a lot of the complexity associated with modeling these systems, doing measurements in the subsurface. And as a result, that means an installer has a relatively easy time of, if a customer comes to them and says they want a geothermal heat pump system, to produce a standard design and deploy that. That's one, and as a result, costs can come down because standardized approaches can be done. In the state of California, because of the complex climate zones and the complex geology, it means there is more effort that has to be put into designing the system. It has made it more difficult to come up with cost estimates. So those things have contributed to the complexity of getting these systems installed in California. And one of the things that I think is important to realize is that from a customer's point of view, we've had many interactions where the response has been something like, wow, that sounds awfully complicated. Do we really have to go through that? Gee, I think I'll go out and just get an HVAC system off the shelf at Home Depot and plug it into my window. That seems like a much easier approach. And in some respects, of course, it is easier. But on the other hand, energy efficiency is lost. There are comfort issues that geothermal heat pumps, I did not talk about, but geothermal heat pumps consistently provide. And many people who use them comment about the fact that, while I did not know it was going to make such a difference, not only in terms of my electrical bill, but also in terms of the comfort in the home or the building. And so they have in the past been complicated systems. And I think for the consumer that's been an issue. That is changing over time. And especially now, I think as more experience is gained in these systems and as their efficiency goes up and design costs go down and installation costs go down, they'll become much more popular in the state of California.
One of our participants also noted that there are more drillers, installers, and designers in the Midwest and Northeast, and whether it's the chicken or the egg, I'm not sure, but I think that should be noted. There's certainly not as many installers here in California. I'm going to try to combine two questions here that talk about payback and cost. Do you have more specific cost figures for geothermal heat pumps? What is the range? And what is the payback period based on energy efficiency? What is the payback period for the system?
The study we did for the state of California, we did not look specifically at cost. But the study we did for the Department of Energy, for the national study, cost was a critical element in it. And there are specific analysis for California for several of the metropolitan areas. I highly recommend you look at that report. But to summarize, the payback time, it's my recollection, the payback time for the state of California, at the time we did that study, was on the order of 8 to 10 years. Because of improvement in efficiencies and lower costs that have been achieved over the last few years since that report was done, payback time, I'm guessing now, the payback time probably is closer to on the order of 5 to 8 years in most places. If you go into the regions where heating is the dominant load, the payback time is going to be much shorter.
All right. What is the best place for homeowners to seek information on local soil conditions and cost range?
The California Department of Agriculture and the California Geological Survey have very detailed maps of soil conditions for around the state, extremely detailed. So it is possible to get information about that relate to the relatively shallow conditions. Conditions in deeper levels, which is really what most people are going to be interested in for these kinds of installations. If you're going to be doing a borehole type of installation rather than shallow trench or slinky kind of thing, that information is more difficult to obtain and is more limited. But there are a number of resources through the U.S. Geological Survey where that kind of information can be obtained. And what was the second part of that question?
Sorry, I'm trying to manage all of these. The second part of that question.
Yeah.
Sorry, I already moved it into the answered category.
I apologize.
We'll hope that was answered.
Okay.
Okay. When was this study done, and when was it published?
Study was made available publicly last year. It was completed 3 years ago.
Let's see here. Another question. We understand that energy savings are not as great during cooling than heating, but would like to know about the zero net energy difference.
If one is trying to seriously achieve zero net energy, it's really clear that a variety of issues need to be addressed. If one is starting from the initial construction of a building, then obviously building insulation, building orientation, building construction materials and style, all those things need to be fundamentally appreciated and incorporated into whatever the design is going to be. And on the basis of that, the load calculation can be done in a very highly refined way. If one takes that approach, then a geothermal heat pump system, if one is trying to achieve zero net energy, it should be an integral part of what that design is going to be. the energy consumption for heating and cooling will be minimal, especially if building design is very, very high quality, and the ability to achieve zero net energy. And I'm assuming one is thinking holistically about this, not zero net energy in terms of just the geothermal heat pumps. It can be achieved very, very well. These are powerful technology. This is a powerful technology. It's highly sophisticated. Even though it's very, very simple in its functioning, it is the most energy efficient means of heating and cooling buildings. The Department of Energy has done a number of studies on heating and cooling technology. Geothermal heat pumps consistently come out on top by a very wide margin, and their efficiencies are improving all the time. They have a long way to go to become as efficient as possible, at least in terms of the theoretical possibility, but they're making great strides in getting there, and they're way ahead of anything else. So in terms of zero net energy, from everything we have seen and looked at in terms of heating and cooling buildings and the technologies that are available, these are by far the most important technology to employ if one wants to truly achieve zero net energy.
Great. The next, are we on slide 16? Yes. The next question has to do with why in climate zone 14 are the efficiencies or the percent in energy reduction so much greater than that of El Centro? What's happening? What's the difference between those two to make it such a great?
The China Lake region has a much greater heating demand during the winter than the El Centro region. That's the principal difference there. It's that kind of, even though they're both in that southeastern part of California, the climate characteristics are significantly different.
Yeah, it's also important to note that those that may not be familiar with El Centro, it is the Imperial Valley. So if you've been in the Imperial Valley, it's very, very hot there. And like Bill said, there's not much need for heating. Let's see here. Is the transfer of heat improved in wet or saturated soil versus dry soil?
Absolutely. Thermal conductivity is a sensitive function of how much pore space there is in a soil. If the pore space is filled with air, air is a very poor thermal conductor. And so a dry soil where there is not much water present essentially is an insulator. It's not completely an insulator, I shouldn't exaggerate, but it conducts heat poorly. A wet soil where the pore spaces are filled with liquid water, which is a very good thermal conductor, provides much greater thermal conductivity, so a wet soil ends up being a much better thermal conductor.
Thank you. The next question, do you have any sense about what the potential penetration of geothermal heat pumps in California might be in the year 2050, both in terms of residential and commercial sectors?
That's a very difficult thing to project, but because the history in California of geothermal heat pump installations is very bleak in the sense the growth rate has been very, very low, and the total number of installations has been very low. However, over the last few years, interest in geothermal heat pumps has exploded, and the growth rate in the industry, I don't have the most recent numbers, but the growth rate has grown substantially. I hesitate to make any prediction about what the percentage penetration would be of geothermal heat pump systems in the HVAC industry for the state of California out that far, but I think it would be substantial. And one thing that is important to realize, that many of the installations that are being done, that have been done in rural settings, relatively low population density. But what's happening is more interest in high-density regions is taking place. And if areas such as the Bay Area or the Los Angeles region become centers where geothermal heat pump installations begin to grow significantly, the impact growth rate could be tremendous, because I think eventually people will begin to see the benefits of these systems, and they'll want them in their places too.
Great. That is a hard thing to predict. Another question here, and I will mention, someone has been writing in reminding us to mention the IGSPA, which is the International Ground Source Heat Pump Association. They have a website that has, a lot of background materials, and there's also been a number of studies published in the last few years, one from Orno, so you can search the web for those.
Yeah, and just to add to that, IGSPA is a tremendous resource. If you're interested in information about geothermal heat pumps, whether it's the design of them, the functioning of them, the issues that need to be considered when putting them in, IGSPA is the premier site to go to for gaining that kind of information. They are sterling, and I apologize for not mentioning them earlier.
Yeah, I believe you can also look up designers and installers there, people that are certified through them. Can you give any examples of rule of thumb numbers for small-scale installations? I think the question here is there sort of an average ambient temperature at X depth?
The state of California is so complex geologically and from a climate perspective that it's very, very difficult to do that. And I would hesitate to say anything other than broad, qualified description of that kind of thing. I think the best thing to do, usually in the various climate zones, there are installers that have installed systems like this. If you go to the internet and just do a search for geothermal heat pump systems in California in your area, usually you will find somebody who has experience in the area, and they can be a good source of information of what you could expect the design to look like, what the loop length is going to be for a given building size, and give the properties of the environment that you're in.
All right, wonderful. We have statements, but not so many questions left. There is one regarding efficiencies and technology. What are the principal losses and inefficiencies or inefficiencies for geothermal heat pump systems? Do you foresee any technological advances to reduce those losses to make geothermal heat pump systems more efficient?
There are several things. One, if you look at the coefficient of performance, the COP numbers for geothermal heat pump systems, for a number of years they were around 3 or 4. What that COP is the ratio of the amount of heat energy made available versus the amount of energy consumed. So an energy COP of 3 would mean that 3 times the amount of energy is provided to the room or the building than was consumed in getting that heat energy there. The COPs are now approaching numbers on the order of 5 and 6. They're getting high, and there are a variety of things that are being done for that. One is the energy required to power the compressors is dropping because the compression systems are becoming much more efficient. Another thing that's important, and it's not often figured into a COP, but it does have a big effect on what the overall energy consumption is of these systems, is how much energy is required to pump the fluid through the loop that goes into the ground. Those pumping systems are becoming much more efficient, and that's one place where important contributions can continue to be made. Another is in the loop design. There's a lot of fluid friction in pumping these systems, and being able to come up with loop designs that minimize resistance to flow is another important element. Also, being able to come up with heat exchange technology that both improves the efficiency of extracting heat from the geothermal loop that goes into the ground, as well as extracting the heat from the heat pump and putting it into the room or moving it back into the loop, those are places where significant changes in technology are likely to occur. The last one, which is, I think, going to be something in the future that could be tremendously powerful, but it's a significant technological challenge. As has been mentioned a number of times, geothermal heat pump systems are most efficient in heating mode as opposed to cooling mode. One of the reasons that is the case is that extracting heat from the room and putting it into the heat pump is one of the low efficiency steps in the process of how these systems function. Improving the efficiency of taking heat out of the air and moving it into the geothermal heat pumps is one area where, theoretically anyway, big advances could be made.
All right, and there is a note in here that is certainly worth talking about, that utilities are now considering owning the geothermal loop field to gain the renewable energy credits, in order to take the cost of the loop out of the equation and make the systems more cost-effective for homeowners. That's being done, I believe, in Maryland. I will note that other states, if you go to the Desire website, it's dsire.org, you can look up incentives by technology for solar PV, small wind, geothermal heat pumps. And some states do have incentive programs. Some it's a refundable tax credit, and sometimes that's based on the tonnage of the system. Some are just sort of a flat rebate, or there are these sort of creative financing opportunities in some areas. So in California, there is no investor-owned utility rebate, which is how most of the renewable energy incentives are administered, though there are some smaller utilities that do have incentives, and that's certainly something that would help move the market forward as it has for other renewable and energy-efficient technologies. With that, we are coming to the end of the hour, so I would like to thank Dr. Glassley and all of our participants for some very good questions. Again, you can go to policy.ucdavis.edu, and if you go to the webinar section, you will see a list of webinars by category. Go to geothermal, and you'll see this webinar. It'll be posted as a YouTube video later today or tomorrow. A policy brief also accompanies it with some of the key highlights of the study, as well as the slide deck and the paper that this was based off of. So thank you, Dr. Glassley, and thanks to all of our participants. If you have additional questions, you can email me, Elise Brown at ebrown@ucdavis.edu, or Dr. Glassley directly.
Thank you.
Thanks, everybody.